Okay. Well, this is the lecture that's going to attempt to explain a lot about the formalism of classical mechanics, in particular how it is due to wave phenomena that you have learned a little bit about in your quantum mechanics courses. Before we do that, though, I want to say a little bit more about phase plots, which is the trademark of the Hamiltonian method. The Hamiltonian mechanics having momentum and coordinates as the independent variables makes for plots in which a coordinate and a momentum are plotted next to each other. Now, we've already seen this with respect to the phasors that occur in our oscillatory, two-dimensional oscillatory model of the inside of the sophomore physics Earth. So here is the original phasor going back to the Irish mechanics of Hamilton. Let's take a look here at perhaps the simplest example of the simplest non-trivial example of the Hamiltonian method and way of looking at things. Before I do that, I should show you three geometries that we would use if we were talking just about a pendulum in gravity. So the force geometry here is shown by a weight vector, mg, that you're probably very familiar with from Physics 1, and certainly any mechanics course that followed that would be remiss in not talking about the pendulum. So you've seen already the component of the gravity on the gravity force in the direction of motion, which is a circle here. And the fulcrum is right here, and we're taking the simplified model in which all of the mass of the pendulum and its shaft is concentrated right at the end. So that is really enough for us to get started with the equation of motion. The potential here would be mg r, r being the radius, cosine theta plus a constant, wherever you want to set your origin for this. I'll let you write this. Now, I would make sure that I point out the things that are very common sign errors that occur in problems like this, and certainly a problem that can show up on a qualifying exam with something else attached to it.
Dr. Harter?
This minus sign here.
I have a question. Usually, we always write the differential equation of motion for the simple pendulum in small angle approximation, but we assume that theta is small, right. Otherwise we cannot solve the differential equation exactly.
And that would just be the good old oscillator.
Yeah, oscillator equation.
Yeah, you'd have theta dot squared here.
Yeah, right.
Okay, and then you'd have theta squared.
Yeah, because if theta is small,
and so
then
this is a parabola, right?
Yeah.
Up to about there. Pretty good approximation for potential.
Like my note was like, if theta is small, sine theta goes as theta minus theta cube or something. So we ignore the second term, we just take the first order term and then write it. Wherever we have sine theta, we just replace it by theta. Cos theta goes as 1 minus theta squared by 2 factorial plus 1 and so forth. So if we don't include the second theta squared term for cosine theta, then we would end up getting a constant potential energy which doesn't carry any theta dependence. So when we
Right. That's just that constant corresponds to where do you want to show your zero for energy.
okay.
You say, I want to set it here, then I've got an extra term. I want to put it so that the energy is cosine of theta is 1 minus theta squared over 2. So that's going to give us a parabola in terms of this. But the other thing you should probably notice is you can also write the equation is in terms of arc length. I'm going to talk about that sort of thing later on. But the Lagrangian would have put a minus sign right there. So, and I'm looking at this thing and I'm realizing, just as an example, I actually did this intentionally. When we talk about Hamiltonian, we put a plus sign here. This is the Lagrangian. Okay, that I'm stating here first. So I have a plus cosine theta for the Lagrangian, a minus cosine of theta for the Hamiltonian. Okay, so be aware that those signs have to be watched carefully. So beginning a problem, always start off slowly. Write things very carefully at the beginning when you're taking an exam. It's important as a qualifying exam. Later on, when we talk about this in Unit 4, we'll mention the other geometries. Here's a Thales geometry for energy. Remember the geometrical mean of this distance and that distance is this distance right there. That lets you write a Euclid mean product of h and the 2r minus h, which is the distance from there to there. That is very nearly equal to 2hr. This is something that we can use to make a nice approximation for the energy. This is what we will be talking about when we get to talk about the elliptic functions. We're not going to do that with this very simple review part of this, of Unit 1. But the coordinate system here is one that's very convenient for doing that. Now, the thing I want to show, though, is three-dimensional geometry of this thing. You can see right away that if I have this being Hamiltonian as constant and call it the energy, and that's what it is, very obviously in this case, then I immediately solve for the momentum as a function of theta. So this type of problem with just one dimension, one degree of freedom, Hamiltonians, gives you an immediate solution for the momentum. To get the actual coordinate functions, that's where the elliptic functions come in, and we're going to see those today in the simulations. But for now, I just want you to look at the phase space. And so what we've done here is plot the Hamiltonian function sort of up and out of the board, out of the screen here, and in the background we're plotting a two-dimensional phase space coordinate system consisting of the actual coordinate angle, and theta equals 0 would be along that direction there. Then as theta gets over to pi, it would be on the other side. So right at this particular point is an interesting point for the pendulum. When I take theta all the way up to pi, that means I take the pendulum from the bottom, which is this stable point, and balance it on its fulcrum. And the thing that you should see is that when you plot this function, just using, this case I think it was the graphing calculator that used to come with all Macintoshes, very powerful graphing formula.
Dr. Harter,
And then I pasted this function here as constants. These curves here are constant values of the Hamiltonian topography lines, if you will.
So which means the saddle points, do the saddle points correspond to
Starting point here.
where the derivative of the Hamiltonian with respect to say theta is zero, like it vanishes?
That's right. But it's also derivative 0 here.
Yeah.
So those 2 points are points in which no force, if you get exactly on it, is 0 force. And if you could really get it exactly on this one, it would stay there. This is the, we're going to see how hard that is to do and how hard it is to make it stay there for a long time. But certainly down here, no problem. That's the way pendulums come from the factory. Put them on the wall, call it a first day. So this is the way that you can understand the motion, and you can rewrite Hamilton's equation in an interesting way. So it's being done here. It's called a funny way to look at Hamilton's equations. Remember, the velocity is equal to the partial with respect to momentum, the slope in the momentum space of h, and that's the q dot, theta dot, if you will, here, and then p dot, that's p theta dot. The momentum dot is minus the partial derivative of Hamiltonian with respect to the coordinate, in this case theta. Okay, so that's that little pair of equations can be written as a cross product of the gradient of the Hamiltonian here. Now the gradient is a gradient involving q and p. That is, it's involving the coordinate theta and the p. So they're the sort of the x and the y in this thing, crossed with a vector that is perpendicular. That's this h-axis right here. H-axis, unit axis, is q cross p. That is, this direction cross that direction. Or right-hand rule would be a vector coming out of the out and up in this screen. So what this is telling you is the vector, whatever it is always going to be going at EH, that's EH here, cross the gradient of this valley. This is a valley in phase space, let's say. But unlike a valley in coordinate space, where if I was over here someplace, the gradient being a force, that is minus the gradient being a force, the gradient is that way, minus the gradient is that way, it would drive a particle down into the valley and it would orbit around. And we'll study plenty of examples of that with two-dimensional oscillators in Unit 4. But this is a one-dimensional oscillator phase space, and what's going to happen here is it's always going to be going, that is, having a force that is along the fall line, I should say perpendicular to the fall line, that is crossed with the fall line. The fall line is minus the gradient of h. So this thing, using your right-hand rule to cross the h-axis with the fall line, that is this vector here, which is minus the gradient. So there's a force this way, and you cross that with this h, and you'll get something that points sort of out of the screen along this line. So what will happen is that you will simply always orbit at a speed that's determined by how big the gradient is. So when the thing is particularly steep, like over in here, it's going to go pretty fast, and then when it gets close to the saddle region, it's going to settle down and be, particularly near the top here, have a very small gradient, so it'll hang up, slow down in this region, and then take off and go fast over here, and then it'll go slow here, then fast here. That's the kind of orbit you're going to see in the phase space.
Dr.
This particular Hamiltonian.
So can we, would it be proper to visualize this as those points where it moves faster? Those are the points in the phase space where the kinetic energy is more, and on the places where the velocity is extremely slow, the potential energy dominates in the Hamiltonian, it
Mhm.
goes back and forth.
Yeah, obviously, when it's fast here, the potential energy is low, right? I mean, the total energy would be low if you didn't have any movement. If I brought it into here and I look and see where I am, you have a negative value relative to this origin for the potential.
So,
You see the cosine right here. You can see where we put the zero. We put the zero where it's usually put for a cosine, right through the middle of its altitude.
so what is that cosine, Dr. Harter? Is that a variation of, so that cosine curve, what does that represent?
Well, this curve, if you were going to construct it out of wires or something, you'd first make a wire that had a cosine, then you'd make another one and put it next to it, but touching this parabola, there's a parabola right here, you see. So it's a cosine crossed with a parabola. You see, this is the parabolic direction. So you'd make a parabolic wire this way and a cosine wire this way, and then you just use them over and over again all the way up the hill, up the parabolic hill. I mean, that's the way you maybe should think about this thing. If you were going to actually make this, you know, we're going to have, soon we're going to be able to you know, program a computer and have something like this cut out. I mean, you could do it right now. If I went over to engineering department, I think I could make this at a certain price, depending on what they charge me. But that's what this thing is you would just cut parabolas, but you'd keep the parabola's nose always following a cosine.
I have one more question. So in this phase space plot, each contour represents a fixed energy, right?
Then, once you've got this surface, you pick it up and turn it on the side, and you saw across at a constant E, right, or constant Hamiltonian, right? Pick a Hamiltonian constant, right, and you get the contours. So all of these curves here are at a constant value of this. So that's the, you know, you're integrating the Hamilton's equation by drawing this surface and tracking where the altitudes are constant. And the most interesting point, the critical points, you might say, are the lines that come right here. So let's, what I'm going to do is go ahead and set up the simulation for this particular Hamiltonian. And this is available, show how you get it from the, you might want to mention where that is. It's called the pendulum.
Pendulum.
And you just click on,
That one for pendulum. We're going to later do cycloidulum.
yeah, that's the one I want to show also today.
So just reference it from your web apps section.
Yes, let's go to the web app section and look for pendulum.
Can I have one more question about it? This is a three-dimensional plot, right? Where P theta and theta are on the plane, and h of P theta is on third axis. So
Right.
if you want to calculate q dot or p dot, you just draw a tangent to that phase space with respect to one of the axes, and that gives you because q dot is partial h over partial p, and p dot is partial h over partial q
With a minus sign.
with a minus sign.
Right. Which is equivalent to a cross between the gradient of the surface
Right.
in this xy space.
Oh no, if I have to view it geometrically, if I want to construct q dot and p dot calculated geometrically from the plot, then do I just draw the tangent?
Yeah, these curves right here are just basically that function. In other words, set h equal to a constant, okay? And then that is telling you where you are for p as a function of theta. So you're making a curve in p theta space using this function equal constant, this constant. This function being a constant, and you're plotting p theta. So go ahead and I guess the thing to do is start off with a very low amplitude.
Okay.
Um,
In fact, I'll just drop it from this
It
displacement.
might be a bit, you remember we can start in the phase space, so
Okay.
always start at P theta equals 0. And you see you make a thing that's very much like a cosine. That's a really low amplitude one. And you can see the periods of those oscillations are pretty much the same. Do one that's just a little bit bigger.
Okay. You say
But
always
make
keep-
sure you stay on the P theta equals 0 axis. There's another one, okay? So you can see that those functions, and do one more that's half the amplitude, but make sure you start at the,
half that amplitude.
yeah, and start always on the axis, so there. Now do one just a little bit bigger than your other one.
Okay.
And you can see it too. There's not so, I don't see any difference in frequency yet.
You see a
But keep-
little,
Just a little bit down there,
a
right?
little bit there.
Now go out a little bit more.
0.75.
Yeah, looks good so far, but then, oh
There
my
you go.
goodness.
Additive.
It's slowed down, right? Yeah, okay, go a little bit more. You're at 1 now, that'd be good one to pick, okay? An amplitude of 1 is pretty obviously slow. At the end there, it's coming up slow. Okay, keep going.
Okay.
1.5, say.
Sure.
Now this one, you can see it's slow after the first wiggle,
Breaks away.
right? And now it's way off, okay? So this is what we call enharmonic behavior. All oscillators that aren't harmonic are enharmonic, and that's most oscillators. Very seldom do we get to play with a perfectly harmonic oscillator like an electromagnetic cavity.
So, Dr.
And
Harter,
there it's really slow.
when you say an anharmonic oscillator, does that mean that you have higher powers of potential?
That's right, that means that the motion will have other Fourier components. And one of the things that's being shown in this program here is very modern. We do this with everything we can. That is the Fourier transform of the momentum and the coordinate. Okay, go ahead up to 2.5. And each time he starts this over again, the Fourier transform starts over. And I'm interested in the Fourier transform that we get when we get real close to the saddle point. But you can see the pendulum swinging there and hanging up out at the end. Okay? Go for a little bit more
Okay.
amplitude.
I'll go straight to 3 and then we'll...
Yeah, 3 is already going to be... And now we are plotting elliptic functions in all their glory. Elliptic functions are harmonic functions in coordinate and derivative, and they're a subject of great mathematical interest.
Dr. Harter, like if we have, if the potential is of the half k squared, we say it's a simple harmonic oscillator. If we have a half k
Yeah,
x
if I
to the
just
power 4,
extended this one out as a parabola
right?
in both directions,
Uh-huh.
okay, then I get a circular trajectory all the time, and it's absolutely uniform velocity around these curves. This is definitely not that. As soon as your amplitude is beyond about a half there.
So can the
Okay.
potential of an anharmonic oscillator also have odd powers of x, or should it always be even powers of x? Dr.
Say that again?
Can the potential energy of an anharmonic oscillator have terms which are odd powers of x, like kx cubed plus x to the power 5 or something like that, or should the potential always be even powers of x, like x squared plus x4 plus x to the power 6, so on and so forth?
Right. You take any potential and expand it with Taylor series,
Okay.
right? To pick any function that has a bottom to it
Mhm.
and expand it. That we're going to study in great detail when we go to the complex variable chapter. I mean, that's something you need to see, is how do you make say, this thing out of polynomials. You know how to do it, right, algebraically, but what's it look like? So we'll study that later on. Okay, we're going to go for the extremes. Go out there and be really careful and see if you can get the thing to be something less than 3.14159.
It's off the screen.
And
There we go.
I see you're having a little trouble because it's
There,
okay, let her go.
145.
Uh-oh, you went on the other side.
But at least it's still
See,
cyclic.
he's looking, you know, if you get it even the slightest bit off of this thing in this direction, you take off this way.
It's
And
easier,
that's what happened.
easier to do it up here because I can see the numbers better, and as long as I'm, yeah, that had some velocity.
Up.
There we go. Twitched at the end.
That's pretty good. I think
That's phenomenal.
I'm amazed that I've never gotten one to be,
Right.
you know, sitting on the top for so long. And that is incredible.
I held my head just right.
Yeah. Well, now you have to go just a little bit to the left of that. Well, oh, I'm sorry, to the right of it.
All right.
Yeah, that's the trouble with doing that one up there, because all you got is position.
I can actually extend it a little bit. It's fixed to be in a circle, so I can get
Yeah.
off to the side.
Okay, try that.
And it had a little residual velocity.
There you go. And you can see that period is almost 3 times, well, at least twice what the other one was.
That's right.
And it really hangs up each time. And it's just inside this oval.
So it's right across.
That's good. Now, you might go ahead and start a few in the phase space. Yeah, and you can look at the Fourier transform.
See how it used to,
Yeah.
when we were really small motion, we were right at one unit at a time. Now look how far it's dropped down.
Yeah. And the curve that you're making with elliptic functions is very close, and it's starting to be a square wave. And these functions are very important in Bose-Einstein condensates. They are the wave functions of the lowest modes of a BEC gas. So they're really important. Instead of having sines and cosines, you have these sn's and s's, Cn and Sn, which describe your gas wave function. It's really an incredible theory that arises out of that. Now, the unstable solutions are equally interesting. You can use a phase space to get this. Just go over to the left and go above
All right.
so that it'll go all the way. Yeah, there's a typical.
Sure, I see what you're saying.
Just go over to the left and pick a thing.
That's
And
Unbounded.
immediately do the other one. Now it's rotating around. You can go down there, but you won't see it because it goes the other way. See? It goes the other way. These guys all up here go this way because of this formula, okay? Right-hand rule, and then this one, all of them go this way. So they're all going left to right, and all the ones on this side are going right to left.
Doctor, what is that function? Like it seems to be like a decaying sinusoidal, something like a function that on the green plot over there.
it's
The green plot is
That's
Fourier
what-
transform. What you're seeing is a transform of something that is...
unbounded function.
Yeah,
This is an unbounded solution, so it's
yeah, so
constantly
it
updating.
gives you a weird Fourier transform. Yeah.
When you say unbound, you just take
Unbound.
all the frequency components, like all the way from
The
minus.
amplitude goes forever.
You can see how it zooms way
This
out
is
there.
this is a compact function. It stays always at home, right?
Right.
This one's going to go all the way to Fort Smith,
Oh,
around
okay,
the
I
world,
get it.
and we
Okay,
won't.
okay, yeah, yes,
You know, we wait a week or so to come back over here.
So cyclic inside and
Yeah,
Right.
non-cyclic on the
yeah,
outside.
it's gone.
So the Fourier transform of that cyclic, the function would be like of a constant sinusoidal function of constant amplitude. Is it like this?
Yeah, all of these up here are basically rotations. And all the ones down here, you can see they come the other way. So there's your map. That's what we're looking at. And I'll just go back here to one of our nice oscillators. Okay, so that's the phase map.
And E sub H is straight out of the page.
And this is what you want to get in any question with mechanics problem. Fine, you get the solutions, but you want to look at them. You want a road map, right? This is a road map for the pendulum problem. And in more advanced classical mechanics problems involving more degrees of freedom, say two coupled pendulums, we're going to have phase plots for each pair of coordinate momentum. And they're going to play with each other. Very complicated four-dimensional geometries result from that. And that's, of course, what people that design accelerators have to deal with. So I claim that the really hard physics, the physics that really has to be precise at the Hadron Collider, is the people that design the accelerator. It's always been true. The other guys can get away with two-figure echoes. Those guys, they need a lot more to make the thing work.
Unforgiving.
Yeah, it's very unforgiving. Yeah. So this is a picture of the simulation. Now we're going to go next to this, but here it's all labeled, and there's the website for this application that TC's programmed in HTML5 from an earlier one that was in Pascal. I think this one was in Pascal. Yeah. So anyway, this particular one showing a little bit of the Fourier transforms too, but you saw them get a lot bigger. Basically, this is very close to the Fourier series coefficients, where we have something at a frequency, then 3 times the frequency, then 5 times the frequency, and then 7, and you can't see much on this one at the 7th harmonic. But alternating in sign is the Fourier series for a square wave. So the Fourier integral and Fourier transform will, as we'll explain in Unit 4, mimic that, and this is a derivative of this, roughly speaking. So that's you know, the Fourier analysis is something you also want to get chummy with if you're going to play with oscillating things. All right, I think the next one that we want to go to is the pendulum and cycloidum. We've given this name cycloidium. Cycloidulum. We got the pendulum and we got the cycloidulum. The pendulum is being done in a nice cosine thing. The cyclo.
Set it up there.
Cycloidulum is being done as something, as a mass not in a circle. There is a circle at the bottom approximately, but this is a cycloid showing right here. And so let's do the same trick with this cycloid, starting with very low amplitudes. And in this case, I want you to notice that you're starting right off there.
Sorry about that. It was a preset.
Yeah. But you can see that.
A small one first.
And make sure you start on the axis.
Okay.
Let's go ahead and erase as and start again on that. Yeah. So there's a low amplitude oscillation. So this is just harmonic motion at the center that you're seeing over there.
If we let it run, period of 1.
So Dr.
And you can see that you've got the Fourier transform popping up at just one frequency.
Dr. Hunter, so you saw that one, the curve on the top right, theta versus time, that's a proper sinusoid, and is that the reason why we get a proper circle in this omega versus theta plot?
Yeah, that one is very close to a sine wave, just like the one over in the pendulum world was. But this one is maybe a little closer. But neither of them are exactly a sine function, or cosine in this case, if you're using the origin that TC is set. Go ahead and get a little higher amplitude.
Just go in intervals here.
And as long as he stays on the axis, that doesn't have any initial conditions, that one should have the same zeros exactly.
Zero cross.
That's what's the magic of the cyclopendulum, cycloidulum, is the, and this is, not cashmere. Now I've blanked out the famous physicist Huygens.
So,
Christopher Huygens, okay,
Doctor,
is the one that was trying to improve the timepieces that were in the laboratories in Cambridge, and at the time that this sort of mechanics was, the science, and he didn't really solve this problem until a year before he died. He lived pretty old, like 78 or so. It's pretty old for people in those days. Very few people made it to 10 in those days. But yeah, go ahead and increase the amplitude a little more. See, what it is that he finally did was he showed that if you could force it to follow a cycloid, that you would get a perfect
I have a question.
oscillation. The
If two
frequency
sin-
always the same. No inharmonicity in the frequency.
So if two sinusoids have zeros at the same set of points, does it mean that they are in phase, they're oscillating in phase? Can we conclude that they would be in phase if they have the same zeros?
I guess I'm not understanding your question. You say if
If two sinusoids have zeros at the same, if they have the nodes at the same set of points on the time axis,
which they appear
which
to
they appear to
on
have,
that graph.
yeah. So then can we conclude that those two sinusoids are oscillating in phase if they have the same nodes?
Well, you remember that he's changing the amplitude each time, but yes, you can. If you had two cycloids swinging, one of them at a small amplitude and another one at a large amplitude, they would keep time, they would keep their phase. Now over on the wall, and maybe we should go ahead and show the picture of what we're going to be studying in Unit 4, the actual device is way over in the corner there. And what you've got with this device, and I'll go ahead and turn the lights on so that the camera can pick that up. What you've got is a string that wraps around a bunch of pins that are on a cycloid. And this is also Huygens' discovery, as far as I know, that if you wrap a string around the cycloid, as PC is pointing out there, it will follow a cycloid down to bottom. So
Copies.
this is called involute-evolute symmetry, and it's a pretty rare thing. There aren't very many curves that are their own evolute or involute, but that's what's going on here. Now, one of those dots is attached to something that doesn't wrap around the thing. The one inside, the lead weight on the inside, does wrap.
Okay.
You see?
I saw it.
So one of them is following a circle, and the other one is following a cycloid. The circle and the cycloid are really close to each other. We'll study all this later on. But the thing that is cool is, yeah, and that's the way you test their frequency. See, one of them's getting ahead of the other. See, they're not quite in sync. One of them is the pendulum we just looked at. It's the slow one, and the fast one is the cycloid. The cycloid is keeping time, same frequency for all amplitudes. And that's, yeah, you can see right away the cycloid gets ahead of the pendulum. Pendulum's slower at higher amplitudes. So by pinching the pendulum, that is making it bend, you speed it up. And you speed it up just perfectly. Now, so, as I say, Huygens didn't discover this elegant solution until very close to his death. Then all of a sudden it just must have come to him in a great flash, and he realized what an amazing clock we have here that you could make. But he'd already solved the problem for the people in the laboratory because he used two circles to pinch a metal band, and that helped keep the pendulum in time.
Dr. Harter, so for
So they only swung about this far, and his solution to that was, a major advantage for the physicist that you're using these as timepieces.
so for a pendulum, that length is a constant, L is a constant, whereas then for a cycloidulum, L is not a constant, right? There's a torque that
You shorten the
it bends.
effective L as the tangent point moves out, and we'll go ahead and show
The
that.
string length is fixed.
Right.
It's constrained though from above, or
Yeah, go ahead.
constrained to
Turn
follow the bottom
fluorescence on the
cycloid.
right.
No, but still,
On the right.
there's a curve that you
Yeah.
bend the
Those
thread
at the bottom.
right
are
for a
two buttons.
cycloidulum,
Push one, then push the other.
which means it torques, the string torques for a cycloidulum. Like it's not
That's
straight.
what
There
that
is a torque.
Correct.
So in that case, so
It wraps.
it wraps, right? So how do we write the equation of motion for a cycloidulum, Dr. Garfield?
You're gonna find out.
You should get the answer.
That's gonna be your problem.
Oh.
But you've got time to think about it. Unit 4 will be along
Oh, okay.
in several weeks. Yeah.
I'll run a few more of these out.
So he's gonna crank it up to the end, and
Let's
look at
put
that
there.
phase pattern. Now this is one that doesn't have anything worth looking at outside of the thing, but go ahead and see how close you can get down at the right-hand side there.
3.1. See if I 3.141. Uh-huh.
Let's
But
try it.
I'm a little bit above the axis. That'll hold. Oh, it went off the other side.
Yeah, you went too far.
Rounding error. There we go. When I moved it down, it slipped its value. Oop,
That's
there it
good.
is. Big jerk there.
Look at that thing.
Right.
Now, when it's in this mode, and this is something else I'm going to ask you to work out the details of, the cycloid is so much a part of the early classical mechanics that it's really quite amazing. What I'm going to ask you to work out will be a solution like this, but with all the geometry that goes with it. And why don't you go ahead and stop the thing and turn on the circles just so people can see what it is that's behind this. The geometry behind this is really quite amazing. So let's reset the variables that allow you to put the circles on the cycloid. So go ahead and
Okay.
show the
Gotcha.
controls, and we'll turn on
So there they are.
cycloid circles. Cycloid's made by a circle, so where is the circle in this particular thing? And there you see it. One of the cycloids being made by the first circle rolling on the ceiling that goes through the number 4. And then the other cycloid is being made by one just like that, rolling on something going through the number 2. So these are wheels hanging from something above, making cycloids that are upside down relative to cycloids you make by just putting a dot on your car tire and then tracing its motion down the street. These two work together. You see the string goes through their contact point,
I'll pause it
and
and I'll
what
put
we're doing is we're looking at,
Here's your contact.
there's the contact point of the cycloid, but then there's also the contact point of the circles, which is on line at the altitude 2. Go ahead and let her run again, and stop somewhere along, right there.
It's gonna go.
Or you can slow it down.
So
you
it'll
can
start
trace
it up.
Yeah. So that solution, and what is being made by cycloids, cycloid is being made by a circle that's rolling at a uniform rate. That one's not uniform. But as you get closer to the limit, then the circles are traveling at uniform velocity. And then all of a sudden, bang, they make the end curve go down here and point it out.
I was trying to with the mouse, we don't have the control.
Go back out to 3.1 and click that. That may be too much. Yeah, that's good enough. Just let that one go.
Okay.
You see that this is constant velocity, positive velocity, negative velocity, and then it has to reverse. So those circles look like they run into a wall. Bang, bang, but in between they're uniform. Very nearly uniform. You can see by how straight the curve is at the top. And it's very nearly uniform, very high acceleration at that point on either side. And what we're making here is a sawtooth curve. So the Fourier series for a sawtooth is being displayed. And its function, instead of going 1 1/3, 1/5, goes 1 1/3 squared, 1/5 squared. So you don't see the harmonics very predominantly. It's not a square wave, it's a triangular wave, a triangular trace. Sawtooth is a common name for engineers for that function. So this is a nice introduction here, I think, to the beauties of the Hamiltonian phase plots. And I have one other demonstration which I think we have time for.
Dr. Harter?
Yes.
So is there any real-world physical system that can be modeled as a cycloidulum? Like we...
Well, I just told you one, except that you don't use the cycloids to look at it, but the BEC is a really good one for the pendulum. For the cyclopendulum, cycloidal one.
Balloon on a wall, on a ceiling, get static on a balloon.
Yeah.
And a mass
Well, I've
on
thought
the surface.
long and hard about how to make an actual mechanical model using a can that would ride on a permanent magnet. That was, the permanent magnet would have to be strong enough to support some kind of hoop or tin can, and then the tin can would have to have a string of something really dense that fixed so I could ignore the mass of the tin can. So I'd have to have something like tungsten or osmium, rod, or yeah, it'd have to be a rod if we're talking about a tin can as the mass, you see. And then you could do this starting the thing off at the top, and it's really, I think, puzzling to people that if this thing worked as this does, that the can would roll uniformly to each end. Uniform velocity this way, boom, turn around, uniform velocity that way, just like we're seeing in a simulation.
Yeah.
And of course, it wouldn't quite be that because it wouldn't quite be the cycloid for the center of mass.
Right.
But if you could do that, that would be the closest I can think of where you'd actually have a mechanical representation of this thing. Now, beyond that, I don't know anything that would make a perfect nearly perfect analog.
I have one more question. If you have a pendulum, a simple pendulum, at the extreme point, when the ball is farthest away from the equilibrium position, its potential energy would be mg L cosine of theta, if L is the length of the string. Whereas for a cycloidulum, the rope bends at the end points. So if you have to calculate the gravitational potential energy of the ball at the end points, what would be the expression, Dr. Harter? Because we can no longer use L cos theta because the rope bends at the end
No,
points.
you have to use the equation for the cycloid. And assuming that the mass, red thing in the pictures here, for the cycloid, like this one, is a perfectly point mass. Okay? In both of these cases, a point mass, and we can ignore the string. And certainly with that device over there, we can't do that. Ignore the string, and the little lead weights account for everything. then your potential energy, MGH, would use this height right here,
Yeah.
the y coordinate of the cycloid,
Okay, so it's a x equals
instead
eight.
of the circle. So
Okay.
instead of a cosine theta, which is what it is for the circle, you'd have the equation for the cycloid,
Oh, like x equals 8 times 1
which
minus
is
cosine theta.
basically a theta plus cosine theta,
Right.
right?
So it's basically take the y equation for the parametric equations, like the equation for y in terms of theta
Of the cycloid.
of the cycloid, and for that value of theta, that will give you that h. That height.
That would give you the potential energy. So that's the simple part, yeah. So it isn't that much different algebraically from the cycloid, except that when you actually do the calculus, very different. The other one gives you elliptic functions. This one gives you straight lines, alternating, right? At the extreme case. In between it, it's a little bit more complicated. It's trying to give you straight lines, and they bend over. So, yeah, this is the. Here's something to look forward to for Unit 4, is a more detailed description of this, and other things it does too. Most people know the cycloid as the curve that gives you the quickest time to go from any point to another point that's below it, but displaced by some distance x.
Is that the same as the
It's
famous
called
brachistone
it's called the tautochrone. This is called the brachistochrone.
with Bernoulli or Jacobi?
These are old Latin names or Greek names for equal time and quickest time. This tautochrone. I'm again having trouble pronouncing anything to do with these things. Okay, the next thing, and we're going to try to do this as smoothly as possible, is a problem I've already given you, just to ask what happens to a parabolic potential when you add a extra, well, I should say straight line force, but a constant force to the parabola. Parabola potential and the straight line potential, that corresponds to a force that is constant in addition to the oscillator force. So that, as you found out if you did the problem correctly, corresponds to the same parabola moved over, and you kind of knew that was going to happen. The minimum had to move. The minimum also has to drop. In fact, the minimum has to always follow a curve that has the same shape turned over as the actual parabola. So this is an interesting piece of geometry just in itself. But what we've got here simulated, and go ahead and let's put this up, and we'll try to play with it a little bit. What we're doing is we're drawing the phase space of this force system. And right now the phase space is just circles around the origin, because the electric field is turned off. Electric field is represented by a red horizontal line, which TC, go ahead and drop it just a tenth of the way, something like that. So that gives you a potential that's straight around the parabola. And at this point, you can't see that there's anything very interesting about it, because the parabola looks like it's only moved to the left. But go ahead and take it down a little further, and the phase circles that this thing is going to follow have moved out. So now the thing is oscillating between the turning points of the parabola, which has dropped. The parabola has to drop in order for its turning points to be there where this thing goes through, you see. So the idea of this is that you can play with this thing. When the thing gets out there pretty far, don't get it too far, you won't be able to catch it. But the idea is that whenever it's on the axis, the next time it crosses the axis,
Okay, I wonder.
drive the E field up, until the eye is right underneath where the mass is. Okay, now what happened? Let it go. You see, now it's in an oscillation that is de-amplified.
So is this
You
like-
reduce the amplitude of the oscillation.
Is it a pendulum in electric field? Like you put that pendulum in an electric field, a charged.
That's what he's doing, is basically
Start.
it's something simpler than a pendulum, because we want the amplitude and frequencies to maintain the same. If this were a pendulum, then instead of having those concentric circles, he'd have those ovals coming out to the eye that represents the saddle points. Okay? Well, basically what I'm trying to show you is that by playing with the phase diagram, you put this phase diagram. If I want this thing to move, say, up this way, I would drive this thing over until one of the lines over here crossed it. Then it would drive right up to there, and then I could bring that eye back and catch it out here. You see?
Sure.
So this is showing you precisely what you have to do to move this thing around in the phase plane to various places. It's very counterintuitive, but it gives you a roadmap for doing that. And that's why I call this, after the famous Catcher in the Rye novel that was so much a part of my generation, and I think some people still read it, right, in high school even. Okay, now I've blanked his name out again, Salinger, right, wrote that. Anyway, this is Catcher in the Eye. You have a phase diagram is like the eye of a hurricane.
Oh, okay.
And so what you want to do is get the eye of the hurricane over the actual mass to stop it. Now that usually can only be done if the mass happens to be on the axis. But a better diagram of this would be when I'm moving that thing, it should also have its own phase motion. In other words, I should be able to catch it up above and below the axis. But then, of course, I'm going to have to, have something that will let me do that, and that means I have to have a force that's a vector potential that's, constant or linearly increasing in order to do that. So we may talk about that idea later on. But for this one, we're not putting that complete description in here. We're doing a static phase plane description. So these are just some extra things about phase space that I think you ought to be aware of, because they're the kind of thing that you would need to do quantum control. If you're going to control a wave packet, you've got to worry about not just where it is, but what sort of momentum state is it in. And then you respond accordingly, and such a thing as this would be closer to having success at, putting a wave packet and keeping it together and keeping it from spreading is what we always have a trouble with in quantum mechanics. Okay, now the rest of this has to do with calculus of variations. At this point, I could use the calculus of variations to derive the cycle. I'm going to leave that as a problem. It's a very famous problem. The first one to solve it got a lot of money, and I think it was Bernoulli, not Newton. I was kind of mad because he didn't solve it, but Bernoulli did, and
So was
received a prize
Bernoulli-
from Royal Society.
So
Yeah.
was Bernoulli a contemporary of Isaac Newton, Dr. Harter?
More or less.
Oh, okay.
Yeah. Yeah. There's a picture of them at the Swiss Institute of Technology that I saw this summer, and their neighbors up there on the mosaic. So anyway, what I want to describe here is integrals of the Lagrangian. Now we're going to see what is it that the Lagrangian is measuring or doing to give us our classical mechanics. And the idea of the calculus of variation is to find extrema, that is either minimize or maximize some function of an entire curve, and in particular an integral of an entire curve. A curve described by something that's a function of both a coordinate and a velocity, and maybe even explicit time dependence that we talked about when we derived Hamiltonian.
Dr.
So
Harter,
really hard problem.
when we derive the equation of motion using the variational principle, why do we impose the condition that the function doesn't vary at the endpoints? Like, why is that relevant?
Well, you don't have to use that, and I have a long description of that later on in, that's actually Unit 7, and the details of what we call contact transformation, in which you pick a particular initial condition state and then go to a final state. That is the thing that is the classical equivalent of a unitary transformation that goes from one quantum state to another, a generation of time generator. So the full-blown calculus of variation that is there doesn't make this requirement. Here we do it because it is immediate way to make a very simple equation of motion, which you're going to recognize when you see it. It's Lagrange's equations. But here we're just going over some of the ideas of something that's allowed to vary its value in between 2 points, t0 and t1, but not at those points. At those points I want no variation at all. I want to make sure that I return to that. Now, derivatives, they can be different. Okay, I don't have to have the same derivative here as I do here. I just have to have the function value the same. Okay, and the variables that I'm talking about, you think of this delta q, don't think of it as a calculus differential, just think of it as another function to represent some variation here, presumably a small variation, say just a few pixels, not like what's drawn there with 100 or so pixels. So what we're going to do is we're going to write just a first order, the Lagrangian that results from having a variation in both the actual position, but also the velocity. So we're going to let this curve, change its velocity and its position, change its slope and its location as we go along. But not much. I only want, infinitesimally small variations in order for this to work, because otherwise I'd have to take this series out in second order and third order and so forth. And that's interesting too. We'll get to discuss that later on, at least second order. So what I want to do is I want to replace this guy, the one that involves velocity of the variation. That's delta q dot is a derivative with respect to time of whatever that was. I'm going to be rewriting that just using the product derivative formula with one term removed. That is, subtract the du dtv, which is this. So this is a derivative of the thing called u, and there's v, and then there's u and v sitting inside product derivative. Okay, and when you do that, you get this. Okay, so you'll end up with an integral and then another integral. I'm taking this term outside. It's this one right here, because I'll find something to do with this. I can get rid of this one, and this one is an integral of a total derivative, so it's just this function evaluated here and then evaluated at the upper limit. T0 lower limit, T1 upper limit gives us this function, this little thing here, which I want to get rid of. So the answer to your question is, why do I set this to 0? Because I don't want that thing.
Oh, that boundary term.
Yeah, I don't want any boundary things in this variation expression here.
So, but in the most general case, Dr. Harter, even when we don't impose that condition, we would still end up getting that boundary term. If I don't set delta of q at t sub 0 and delta of q at t sub 1 is not 0, I would end up getting the boundary term. But still, when we get the equation of motion, they should correspond to the same laws of motion.
Well, here's something that's a function of the velocity, or at least a derivative with respect to velocity. But I don't care what this is. This one will kill it,
Okay.
unless this goes infinity, right?
Oh no, I was saying that if the boundary terms, if we don't impose that condition that the function doesn't vary at the endpoints, if that condition is relaxed, then you would end up getting that boundary term, right?
Yes.
But still.
And I also have one at the beginning,
Right. Oh yeah.
okay? And that's part of the contact transformation,
Okay.
okay? But we're not dealing with that right now.
Okay.
See, S is called action because it generates an active transformation. That is a transformation in time. That's the only reason I can think where the word action came from. But I could be wrong about that, but it's the way I remember it's sort of a nice mnemonic, even if it isn't true. But the idea of, this is an idea from Lie, L-I-E, who developed ways of solving differential equations by group transformations. And contact transformations are group transformations if it's done right. So you can think about your motion as various elements of a symmetry group or spectral generating algebra giving you elegant solutions to otherwise intractable problems. In any case, here's what we've got is the original integral S, Q, just plain old Q, and this extra stuff here. And you can see that with that thing gone, this leaves a first order variation of the difference between these two things as that. Okay? Now, you see, we have the ability, we can turn the knobs on any value of time. At any value of the time, I can pop up a variation and then come back down again. So I could have a variation, just followed the original curve and then popped up and then popped back down again, followed the curve to the finish. So if this thing here is going to be the idea is that the extreme value is one which would get this to be 0, this variation to be 0, then this equation inside here has to be 0 everywhere, because at any point I can turn on one of these things and make it non-zero. So if this bracketed thing wasn't 0. So this is a derivation of Lagrange-Euler equation, which is just our Lagrange equation for mechanics. If the S is the action and the L is what we call the Lagrangian function we've been playing with. So this really is kind of neat. Everybody's excited about this. Feynman has an entire lecture devoted to explaining, basically to people that weren't physicists, what is cool about this thing called the Lagrangian. And that coolness is that it goes around minimizing itself on every trajectory. And the question that really asked is, why is nature so inclined to fly, that is, make a trajectory, just so as to minimize this thing called the Lagrangian, T minus U, kinetic energy minus potential? What is the deal here? You see, what's making that happen? Okay? And people were so amazed by the fact that this does happen that they just stopped right there and said, it's a mystery, right? There was, in the classical literature, no talk about what is this, you see. Well, of course there were people that were curious. I'm not the only curious person.
And what is the answer?
And they were worried very much about this. So today, in the next 10 minutes, We're going to give the answer. Okay? What's going on? Right? And there's nothing in classical mechanics up to this point that would suggest the answer to that. Okay? Now to get this answer, I introduced a couple of new things that will be showing up in Unit 7. And by the way, I'm doing them now because it's rare for us to make it to Unit 7 far enough that we can do this. So I'm doing shortened versions of stuff that's in Unit 7. So if you want to read more about this, there it is. And goes on to Unit 8. The Legendre transformation is a secret that we need to unravel. Poincaré's invariant differential. If you clear from this the dt that lies in the denominator of a derivative of r, v is dr dt, okay, this thing. So v dt is dr. This thing right here is simply dr. And I multiplied through dt to make that come out. So this is the Legendre transform differential, if you will. It's really called Poincaré's in differential. These guys were working on stuff and coming up on similar things with different interpretations. So this is a this is what is really called the time differential of the action. This is ds of the action s integral L dt. And this is the integral that we just said is always minimum. So then it boils down to a question, why is the action always minimum? Well, you could make a flippant answer is that's just like any human activity. The activity is always minimum. People always try to do the least, right? So you could just leave it as a sociological anthropomorphic theorem, right? And of course that doesn't satisfy a physicist, but you know, some people would say, yeah, that makes sense. That's nature's lazy, right? But we want better than that. We want some very quantitative stuff here, okay? So we write this differential ds, that's L dt, okay? P dr and H dt, where this is the definition of a Lagrangian in terms of action. It's the time derivative of that stuff called S, the generator of active time transformations, okay? That's what we get later. We jump ahead to where we prove by relativistic stuff, wave phenomena basically, the de Broglie law, which came in 1921 about, it would be almost 16 years after Planck's law. Well, it's 21 years after Planck's law, but after Planck's law got settled in Einstein's work in 1905, it's 16 years. There's a big jump between these two. They both use Planck's constant, and the idea is that the energy, that's the Hamiltonian, is minimum value is h bar times some frequency that in the case of a cold light is the actual cavity mode frequency being looked at, okay? And then this is de Broglie's law, which comes, as I say, much later. And those are the things that kind of tell you what this is. What is this quantity here? This quantity is the phase of a wave function.
Yeah, it's a plane wave. Yeah.
This is k dot r minus omega t.
It's a traveling plane wave.
And in quantum mechanics, man, we like to keep the phase, baby. Okay, so this invariant differential, okay, and we mean really invariant, all possible weird classical mechanical contact transformations that you can come up with that make any sense, it's invariant to those. But the most important thing that it's invariant for our discussion is the Lorentz transformation. This is Lorentz invariant. It's a dimensionless Lorentz invariant. There are lots of Lorentz invariants that have lots of dimensions on them which you might not trust. This one you can trust. Okay? So when you're talking about a quantum plane wave phase, that's what we're dealing with here. Okay? That is quite remarkable. I think that that begins to shed some light on what's going on here. Now, the idea is, can you integrate this differential equation? Is that ds integrable? When is the action differential integral? Well, remember, when is the work integral? That's f dr, okay? fx dx plus fy dy. Forget the z coordinate, okay? We only have two variables here with two there. So when is that integrable? When can you integrate that thing to a function that doesn't depend on the path? Remember the conservative function, so to speak. An integral function is satisfying. And that is when the f of x, force here, is the first component of a gradient, and then when f of y is the second component of the gradient. Okay? When you can write the thing in terms of a potential, then it's integrable. Let's be more strict about our mathematics. This is similar to the conditions for integrating work differential. So dw is f dr, not Roosevelt, but f dot dr. And if you can integrate that to get the potential, and there is a potential that makes sense for the force field that you're asking about, that f, that condition is that there is no curl of that field. And we're going to go over this again with complex variables to see how all of this two-dimensional field theory really makes sense.
Dr. Harter, so that one, that fact that curl of f is 0 ensures that the line integral around the closed loop is 0.
Yes, yes, that's the integral view. The Stokes theorem lets you do that. But we're avoiding that because that's a little layer of complexity. We're just doing this with differentials here. And the idea really is that if you do have a potential that's integral, differentiable, I should say, then it has the partial symmetry we talked about. That is, the partial derivative with respect to y and x in that order should be equal to the one with respect to x and y. That's what would make the curl 0, right? Okay, we want this whole thing to be described by a scalar function. No vector potentials allowed. Vector potentials, then you start getting curly stuff, right? So, we must have that for this differential, okay? So ds is integrable if the partial derivative of s with respect to the first independent variables, now there's 3 of them there really, so this is a Jackson equation, but if you only had one dimension, it would be x, and this would be px, p sub x, all right? And then we got a minus sign here, so the partial derivative s with respect to is minus h. These conditions are known as Jacobi-Hamilton. Okay, you mentioned those before, right?
Yes.
Now the derivation of these equations in Goldstein is like 40 pages, just garbage. Okay? This is the derivation of it. It's one line once you've gotten to the idea of the phase. You see? So this is, you know, we're now getting to the guts of this classical mechanics. This is the most sophisticated classical mechanics equations designed to create families of curves that have certain properties.
Yes, I wonder, Dr. Harter, can you go to the previous slide, please? The previous slide. So we find that, we have Jacobi equations, Hamilton-Jacobi equations. Yeah.
Okay.
So P is partial derivative of S with respect to R, and Hamiltonian is derivative of S with respect to T.
With a minus sign.
With a minus sign. But the thing is, action is integral L dt, right? So if we have to determine
this right here.
Yeah. So we need to know the Lagrangian if we have to determine the action.
We want to be able to close this interval,
Yeah.
actually get a function
So
The-
my
the-
question is,
A
once
definite integral,
right.
yeah.
So once we know the Lagrangian, we can calculate what the momentum is. We can calculate what the Hamiltonian is because that follows from Legendre transformation.
Mm-hmm.
So my doubt is like, in what way does Jacobi-Hamilton equation enables us to get better insight? Because instead of taking the partial derivative of s with respect to r, we might as well use Euler-Lagrange equation to get p, and use Legendre transformation to get.
Well, the dream, you see, of all the people that work with any kind of mechanics or field theory was to find an elegant way to generate, that's what this thing is, this is a generation of active transformations, you see. The idea of it was that if I could just find this generator action, I'd rule the world, I'd be God of the classical mechanics, you see. You give me some initial conditions for this very complicated system, and I just take my action function, stick it in one part, and then read the other one off as time goes on. That was the dream. The dream was to do that. Now, the dream comes apart in something as simple as sophomore physics trajectory problems, because you already have to solve cubic equations to get this. To actually do this, and that's what we need to show the rest of, and I'm realizing now time is a little short for doing that. But what I will do, I will show you that as far as Schrodinger analysis goes, you kind of realize the dream a little bit. The idea is that I can find this thing if on certain things. And I can also use these to, and this is of course an approximation, but I can say if this is my wave function. Now, what's this leaving out? This is leaving out an amplitude that might vary. We just have a 1 there or some constant. Okay? That needs to be put in order for this to be completely right. But for Schrodinger, sure, you don't need it. For this, just try a first R derivative of this wave function. Okay? I take an R derivative of this guy, okay? And that will simply be an R derivative of the exponent times the original exponential.
That's
Right?
Yeah.
And that gives you I over h bar partial s with respect to R. Okay? What is partial s with respect to R? It's P. Okay? So here's your basic idea of quantum mechanics, coming from classical mechanics, so to speak. Here is the operator, you see, that we need a representation of in coordinate view, okay?
Oh, so you assume
That is our P operator.
So you assume a free particle wave function, you take that as your wave function, and then use a Hamilton-Jacobi equation to...
Now remember, this doesn't have to just be one particle, right? This can be a whole configuration space, and this can be a canonical momentum that goes with it. Now time, we don't argue about that, I know what it is, but the Hamiltonian, okay, would have to sit in there. And that one is the other side of the story. And the two go together to make relativity. So this is relativistic quantum mechanics we're doing here, in a sense. This equation right here is valid throughout. It's not just limited to the Schrodinger view. But here you have this wave function, take the partial with respect to time, same thing, okay? Okay? So you have a partial s with respect to t, that's minus h, gives you the right sign, everything's good. Okay? That is an equation that sits several places in this room, but mainly it sits right here. Okay? So this is, a really backhanded derivation of things, but once you understand what you're dealing with, it comes out pretty nicely. Pretty clear. It's the clarifying thing. Now, this is the deal about the minimum. You see, at each point, a wavefront broadcasts in all directions. And you can trace out where that wave function would be using Huygens principles. The idea is that you start with some wave function, and then you broadcast from each one of those according to whatever this action principle demands you to do. And the action principle basically is able to take you from any curve here to a curve over here. But we want to say, okay, well, where did this point go? Okay? Did it go directly to there, or did it sort of go up here and then come back to here? Well, on a differential level, it's supposed to go directly. So the idea is that if you were going to go from here to that point, sure, you could take another path, but then you'd have to, get off the freeway and start taking country roads to get back to this freeway. Okay? That's going to cost you action. That action is going to be bigger than the action that you accumulate by integrating this thing from here to here. Okay? That is really what's the optimal path that accumulates the least, in this case 20 units of action at some arbitrary thing that I've just sort of made up here. A non-optimal path accumulates more, 50% more if you believe these numbers, okay? And because the action is the quantum wave phase, that is, this thing is the wave phase of the amplitude to go from there to there. That's really what Feynman's quantum mechanical approach starts with, amplitudes to be something and then be something else. Be at a certain space-time point and be at another space-time point nearby. Okay? And the amplitude for doing that is approximately, if you can believe that I don't have to worry about the actual magnitude of that thing varying,
Dr. Harter, I have a question.
is this.
So did Feynman define that e to the I s over h bar as the inner product between r sub 0 t and r1 t1? Did he define it that way?
Well, that's what Feynman path integral formalism works with.
Okay.
There's another way to do quantum mechanics. Turns out, horribly clumsy. Horribly clumsy. But the closure relations that you used to in quantum mechanics make sense only if that is a minimum, you see. And basically what is happening here is all of these paths are competing, you see, to get to this particular point. There are all sorts of points. Okay? One goes to China. Okay? Another one goes to China, has a beer, right? I mean, that's the trouble with Feynman path integral formalism. Where do you stop counting all the paths? Over here too, right? Over here and do a loop and come to here, right? I mean, there's no countability, you see, to Feynman paths, unless you define them by group operators. Then the group multiplication table has all paths, automatically. But the job is to minimize this, and the idea is that only near that path will you have very little variation. Any first order, you have no first order variation in this. So every one of those paths will reinforce, pile up wave function on that purple line. All the others are canceling out.
So when you say only minimum action path interferes constructively, which means if the action, if the path doesn't represent minimum action, the inner product vanishes. There is no interference, destructive interference.
No variation in these function near that path. You got to find that magic path that satisfies Lagrange's equations.
Okay, because
SOB F equal MA.
Dr. Harter, this inner product that you have, the inner product between R0 and R1 term, that's the interference term, right? That's the interference between the initial state and some state at a later time.
Right.
So if the interference is destructive, that inner product has to vanish, right? That
Well,
goes to zero, because
if you were forcing the thing to take some other path, I don't know what you get, but the basic idea is that you're thinking about, how did it get from here to here? You see, where is that path? It's only the path that satisfies classical mechanics. The only path that really is going to build up amplitude for you is one that isn't destructive. It has to be a minimum. Can't have first order variation. I can't put another bump on that and still have the same action. So I put a bump on there, and then I put a bump right next to it, it'll cancel it, because I have linear variation off the path. Everywhere over here, all these paths are all fighting with each other, they're all going to end up canceling each other, compared to the mountain that's being built on that purple line. It takes a while to get your head around this, but it's just really quite remarkable. Now, we're going to finish here by how would you actually do quantum mechanics if all you know is classical mechanics, but you kind of heard about these rumors about action and stuff, okay? Bohr quantization you know about requires quantum phase and amplitude to be an integral multiple of 2 pi after a closed loop so that the phase is the same. That's one thing that you learn about, and that's how quantum numbers come by. Whenever you close one of these things, you're going to get quantization, okay? So the idea is that these two equations can easily be integrated. That is, I can make trajectories just by solving ordinary classical mechanics, and I can work out what is called the reduced action, which is the integral, well, it's the integral of L dt plus a little bit of energy, an hd here. This is Hamilton's action. This one has got both space and time in it. These are minor details that we'll work out. But here's the basic idea, is you simply run a classical trajectory, but you color it as it goes according to how much you've got in the integral of L dt. This is a simulation in a thing we call Color U2, in which first made this. But it's based on an idea by Michael Davis and Rick Heller, that they did at Los Alamos while I was there. And I can show you, this is a much simpler example of it, which I will put up on this screen here. If I can find the Color U2, there it is. So this is a picture of a typical space x1, x2 with an oscillator in it. And the oscillator is going around being colored according to the action as it goes. And this one is just the right length so that the colors come back to the same time after several, say 4 oscillations. But what I want to show you is an example. I think it's this one. Actually, that one is a little bit weird, so let me take another one. I think it's at 45 degrees, if I'm not mistaken. No, it's not. It's at 0 degrees, I think, yeah. That's pretty good right there. This is an example, not quite like the one that's shown there, but you see what happens is after a while, if I've picked the quantum initial conditions so that this is this path gives you an integral value to the things that are, and adds up at every point. That is, if I get coherent addition of the action wave function, I will actually see an outline in color of the eigenfunction for this two-dimensional oscillator. This is, I think, really beautiful. I'll try to make the example that, if I'm not mistaken, it's this one. No, that's not it either. Which I kind of got lost. Let's see, omega 0, 45. I'll try this one, 2, 2. No, that's the one that's a very simple Bohr thing. My gosh, where did it go? 2, 1. I mean, all of these are going to make waveforms. This one's got Coriolis forces turned on, and all kinds of weird stuff. Let's try this one, 2, 1. That's also quite weird. That's showing an invariant torus for this oscillator. Is this what I want right here? No, it isn't. Do you remember where that went?
No, I don't. Just
Let's
gotta
see,
go through them sequentially, I guess.
That one's not it. It got lost. There's 2-1 at 90. There's 2-0. That is extremely weird. I thought it was right at the tip of my tongue here, and I don't see it. But in any case, this is an example of what I was trying to get. I have somehow managed to misplace that particular setting. But what you're seeing is an example of the, oh God, that is really
Can we
bizarre.
deconstruct the ABCDs?
Yeah.
Because this appears to be, is that curlless?
Yeah, but then I wouldn't get, these were set so the thing is coherent. It's a quantum state, not just any classical state. And I'm just completely flummoxed by the fact that it won't, oh, there it is, it's right the first one. Okay, this is, yeah. So you see the thing going around, leaving off all of the colors, but now at the nodes of those wave functions will be all of the colors except two opposite colors, in this case red and cyan, which are 0 and pi. So this is a case of a closed system that has quantized the energy, and there are only two phases, plus and minus, for cyan and red. So we're assigning various values of the Lagrangian to, that is the phase associated with the Lagrangian, to colors, and then making sure that we don't just get gray, because that would not be a quantum state. Now if it's an open system like our fountain, then you see all the colors, and you see the wave fronts associated with its motion. And we've got to speed along here a little bit. Here's the fountain happening, but we're plotting the action function equal a constant, the wave front, which goes out, starting out as sort of an elongated circle, then hits the top and makes two sort of bat ears or cat ears here, and this is the top of the parabolic envelope that we looked at, and then this just continues down, making the cat have nothing left but a smile. So this is the, Lewis Carroll cat, which vanishes and everything but his smile disappears. There's the smile in that function. And you should not confuse these curves with the curves that are classical, that is the blast circle that just expands at a uniform rate and the center falls like a ball that was dropped from this point. That's the thing that has what we call group velocity. The classical particle velocity is being manifested here. But you should be aware that the phase velocity of a quantum wave, that is its time derivative of its position, the red stuff here, is just simply omega over k, which is the Hamiltonian over the momentum. So in places where the classical momentum is particularly slow, okay, p is low, or worse, 0, okay, you can expect the k to be 0 as well, but this is not 0. So you have right here infinite velocity at first, and then these things race off here very fast. And this is a region where velocity is pretty low. So this goes pretty fast and catches up with this guy right here where the p is high. P is high from the falling particles. The classical group velocity is the derivative of omega with respect to k. That's Hamilton's first equation, by the way. Okay, group velocity expression is the Hamilton's first equation. So here where the classical velocity is very high, this slows to a crawl. So this gets slower and slower and slower as it goes. So all of the things that we're talking about here that have to do with phase are behind the scenes. They're the unseen heartbeat and lifeblood of classical maths that you're working with here. That we are writing classical equations for, and we only write equations in the group velocity. It's the only velocity we know until we started playing with action. Okay, now I should point out that this color quantization led to a lot of artwork by Rick Heller. And I should ask you to check out the Heller galleries. This is some very beautiful things, just made with waves and coloring them for various reasons. So it goes back to Kolodny, who was given a prize by Napoleon. You can read about that. And it was the Kolodny plates that you play with sometimes in laboratory. Napoleon offered 3,000 francs, that's a hell of a lot of money then, to explain the patterns. And the mathematician Sophie Germain was the one that actually won the prize. Although, as Rick points out, her solutions were not completed until the work of Kirchhoff quite a few years later. By then, Napoleon was in jail, so he couldn't give another prize. But this is, one sort of the heritage to looking at waves with color, which is what Rick has done. And one of his shows was at the University of Arkansas. I brought him here in the October 2002, about now. He came just in time for the biker festival, and he was, since he's mostly interested in sound waves now, I'm sure that he was impressed by that. There's a lot of sound waves going around that day when he first showed up. But I should also point out that as soon as his show closed, the UAF museum closed and has never opened again. Now it's a bunch of offices. So with that sour note, we'll end our description of wave mechanics that applies to classical mechanics.
The part where you discussed why S has to be, the action has to take the minimum path. In which unit have you discussed it in the text? Like this one, yeah. In which unit?
I put this in everything I write because it's so important.
No, like in the text, in a textbook, in which unit is it? Have you discussed?
Yes, this is actually figure 1212.
Oh, it's still in unit 1. Okay, chapter 12.
Chapter 12.
Oh, okay.
Yes. Absolutely. No, I mean, I can't get this out of my mind, and Feynman couldn't either, and neither could Dirac. What's really interesting is that Feynman and Dirac met at one of the American meetings, and they both were writing papers about path integrals, Lagrangians, path integrals, and Dirac had a very elegant paper in which he described many things about the path integrals, and they got together, and from the stories that are told by Feynman, you have to be careful. Sometimes he tends to exaggerate a little bit, but probably in this case it wasn't necessary, because Dirac said, and the thing that strikes me strange, Dick, is that the Lagrangian, you see, seems to be very similar to this integral of Lagrangian seems very similar to the quantum phase. And Feynman says, that's because it is the phase. Well, it isn't. It's h bar. But forget the scale factor. Okay, he was right in that sense. Dirac said, it had an amazing epiphany because he suddenly realized that was the connection. You've got to deal with, keep the phase, baby, instead of keeping the faith. So, the unfortunate part is when you actually work out those curves that I was showing you, the cat ears and the bat ears, Those are solutions to cubic waves. They're a pain in the ass to get. And that's the simplest sophomore physics trajectory problem, right? A bunch of parabolas in a constant gravity field, right? Start varying a gravity field, boy, those things are even more complicated. You're always solving equations to get these things. So the path integral formalism now becomes sort of a, it's a hobby. Various people that work in fields find ways to use it.
Tool.
Yeah, it's a tool, but sort of a hobbyist tool. It helps you get some qualitative features, but usually it's really the hardest way to get the actual waveforms. Now maybe we can change that by doing the whole relativistic thing and doing it with group transformations. That's the way to handle it, because then you know all the paths. All the paths are accounted for. The real problem with this thing is it's not accounting for all the paths. And it's, of course, not doing relativity, which is behind all of this. You're doing pseudo-relativity all the time. Anyway, this is, we're already a significant fraction of the way into this course, but I've arranged it this time so that you get to see the fireworks sort of early on. What it is that's really behind this formalism. What's hiding behind our contact transformations, our intercepts, our slopes, Legendre transformation, all that kind of stuff. You get to see that.
So which means, Dr. Harter, we should be able to even do classical wave analysis using path integrals, right?
Oh, well, of course.
Diffraction.
That's one of the major things that's pointed out in a book by Morse and Fishbaum, Methods of Mathematical Physics, which, in my opinion, is the only book that should be used for mathematics. Unfortunately, it would take 3 semesters to even, do it justice to it. But what they show is they always stop and show what are the things that are being extremized to make this differential equation work. You see, they were so taken by the idea of the Lagrangian, being minimized and then yielding equation of motion. So they take a lot of things like the waves, various kinds of wave equations, various kinds of diffusion equations, various kinds of things that were occupying physics in the time around the beginnings and ends of World War II, which involved vacuum tubes and electric circuits and thermodynamics of complicated systems where a lot of temperature, a lot of heat was involved. And they spent their, lifetimes struggling with getting convenient ways to get those. Without a computer, they didn't have computers that were very good. Calculators, room full of. But they realized that maybe there was a better way to do it by appealing to the extreme calculus of variations. And so, to a certain extent, they did get a lot of insight that way. But it all boils down to doing a relativistic quantum Lagrangian. Really is where we stand right now in our ways of looking at things. So the better we can understand that, turns out you can go back and make other things simpler. We hope to be able to do this for graphene. Finite subgroups of the Lorentz group are approximately the generating groups for the electronic waves, the acoustical waves, and other things.